In this video, we will be covering the trajectory of objects in a vacuum. If you don't know what a trajectory is, imagine throwing a ball away from you. That curved path it makes through the air is the trajectory of the ball. There are three things that define the trajectory of an object in the vacuum. One is the acceleration due to gravity, and in this example we will make it 1 meters per second squared, just to make it simple. And the final two characteristics that define the trajectory of an object in a vacuum are either the vertical and horizontal velocities, or the true velocity and the angle at which it is initially thrown. In this example, we will use vertical and horizontal velocities as it makes things a lot simpler. So, vertical velocity, horizontal velocity. In this example, if we make our vertical velocity 5 meters per second and our horizontal velocity 3 meters per second, we now have enough information to plot out the whole trajectory of this ball in the vacuum. So, if this is our initial starting point, after 1 second, it would have gone 3 meters horizontally and 5 meters vertically. So 3 across and 1, 2, 3, 4, 5 up. It takes 1 second for the ball to get from here to here. Bearing in mind each square represents 1 squared meter. After the first second, the vertical velocity drops by whatever the acceleration due to gravity is. So that is 5 minus 1, which equals 4. So our new vertical velocity, is 4 meters per second. And so we go 3 across, because the horizontal velocity never changes unless it is in an atmosphere, or if there is another force acting upon the object during its flight. So 3 across and now 4 up, and we just keep repeating this until the ball hits the ground again. So 3 across, 3 up, 3 across, 2 up, 3 across, 1 up, 3 across, 0 up. Now we have reached apogee. That is the highest point that the object reaches in its suborbital trajectory. So now our horizontal velocity is 0. Our vertical velocity is 0. But the acceleration due to gravity is still taken away from it. So 0 minus 1 is negative 2. So it goes up negative 1. So it goes up negative 1. So that would be the equivalent of going down 1. And then down 2, down 3, down 4, and then again down 5, and then it's hit the ground. Each point represents a second in the flight. And if you look, they form that curve that you saw when you imagined throwing the ball. If we change the horizontal velocity, our initial vertical velocity was 5 meters per second, if you remember. If we change our horizontal velocity to, let's say, 4, it was 3 before, our flight would actually take the exact same amount of time, because the only thing that determines the time it takes for the object to hit the ground after being thrown is the vertical velocity. So we go 4 across this time and 5 up. 4 across, 4 up, 4 across, 3 up, 4 across, 2 up, 4 across, 1 up, 4 across, 0 up, 4 across, 1 down, 4 across, 2 down, 4 across, 3 down, 4 across, 4 down, 4 across, 5 down. Now, if you look at the two different paths, they not very neat, but they look very different, but they take the exact same amount of time. If you count the number of dots, they're the same. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Because the two flights take the exact same amount of time because they have the same vertical velocity. And that is predicting the trajectory of objects in a vacuum.